All right, so hello everybody. My name is Václav, and I also work for H2O as a data scientist. Uh, and today I'm going to talk about two bigger features that we introduced into our latest major release, 3.22, I think. The code name XIA, Xia. The first is isolation forest, so it's a method for detecting anomalies or outliers in your data. And the other one is the tree API, which is a means how you can work with the tree-based methods programmatically. So how you can basically look into the structure of the trees, how you can plot them. There's obviously more features to this, but today we have time to basically dive deeper into these two, which I believe are really useful. So first, maybe let me say a first few words about why this matters. Imagine that you are, for instance, looking at your data, like at transactions, for instance, like bank transactions, and you want to detect fraudulent transactions. So one way how to approach this problem would be to label the typical fraudulent transactions and calibrate a supervised model. But then the problem may be that this is like looking for a needle in a haystack. There may be too few fraudulent transactions. So it may become extremely costly to actually create the training data set. That's the first problem. And the second problem with the supervised approach could be that the definition of what fraudulent is could be very fluid. It may not be really a kind of crisp, well-defined class what you're looking for. The only thing you are looking for is it just should be really abnormal, right? Like the classic statistical approach for looking for abnormality would be to postulate some density, right? Some model behind the data, like in the classic state, you would say it's normally distributed, and you would then cut off the extremes, right? Could be a very dangerous thing to do because even the extreme cases could be very legitimate cases, right? And you can sometimes see how people cut off what they deem to be outliers, but in fact they are just not observe enough data to see, right, the full continuum. That's one of the advantages of actually working with the full data set, not just the sample, and that's something what technologies like H2O and Spark bring, right? That you can actually just work with the whole data set, not necessarily with just the sample. So what this method does is that it uses tree-based methods, right? For instance, in this case, random forest, and it learns, right? It learns a model just for the purpose of measuring or to produce some score that would give us not the likelihood, but basically as an anomaly score or isolation score that we would use then to characterize whether an observation is an anomaly or not. So how we do this? Or maybe before I describe the algorithm, let me describe the intuition. The anomalies, right, as I showed with the normal, when I said like the classical approach would be to postulate normality and we would look at extremes. So we would still go with that intuition, but we would just make it, we would just make a less stringent assumption about how the data should be shaped. We would basically relax the assumption of normality, and instead of let the data speak for itself. That's what the tree-based methods are good for. So we just basically postulate that the anomalies should be very easy to spot on, right? If something is anomalous, if something is like you know that very well, that if you come into a room that you know very well and then something is different, then you immediately spot the difference, right? So this is the idea. So in our case, we are building the tree by randomly splitting the features, right? Just purely randomly, no gain, no max entropy, any kind of heuristic like with the classical trees. Instead, we are just splitting that randomly, and anomalous observation should be should end up in its separate branch very quickly, right? Whereas if you basically, because it occurs in a very sparse area of the space, whereas the very densely populated space of the observations, you still need to basically recursively repartition. So in our case, like, let this be just the classic splitting points, right? The blue are, or the leaf nodes are the observations, the data points, and the blue ones at the bottom, right? Because they have they are deep in the tree, they would be non-anomalies, whereas following our intuition, they are just described, this one would perhaps be an anomaly. So with this intuition, we can just make it a bit more formal, right? So what we do is that we randomly partition the data and create the trees by randomly choosing a feature at each split, and we take the minimum and maximum for that feature and just randomly cut. So we basically choose a threshold also randomly, and we continue until we basically separate all the data. So for the categorical classes, for instance, if you have in one leaf basically only the same class, right? With the numerical, it just has to be an individual observation. So once you basically separate all the observations into the leaves, right? You are done, and you do that again and again and again. We construct multiple such trees, say 400, 500, 100. This is a plot borrowed from the original paper by Liu, Kai-Ming and Ji Hua, I think. These guys, right? It came out on 2008. So, like when you are partitioning the space recursively, you are actually formulating or creating like a hyper hypercubes, right? Or hyper whatever it's called, the geometrical like hypercubes, I suppose. And you see that in this XY, right, is in a very dense space, so you basically need to do a lot of cuts until you separate it into the leaf. Whereas this guy, which is quite on the edge, X0, you just need few number of cuts. And as you build more and more trees, you can average you can compute the average depth of the observation in the tree, and it converges, right? Initially, there's some variance, but you see this is a log scale, right? Maybe it can't be seen back in the room, but here is 10, here is 50, here is 100, and here is 1,000. So you see that pretty much from 100 onwards, right? It converged. So with this observation, we know that basically when we build multiple trees, the depth is quite stable, but there's another problem, right? I get a number, I get average depth of the observation in the tree. Okay, how do I decide if it's an anomaly or not? Is 5 a lot, or 6, or maybe 2, or what would be a good number? So I would need some kind of normalization, ideally, right, between 0 and 1. But before we go into this, right, I will just give you directly the conclusion. This is directly also from the paper. Basically, the method, as also implemented in H2O, gives you both the average depth, which is not normalized, and also a score, which is actually the thing you primarily need to look at. And if it is close to 1, right, then it's highly likely an anomaly. If you get 0.5 for all of your observation or something around that, there is likely no anomalies in the data. And the same, if it's below 0.5, it's highly unlikely. It's basically in a dense region of the observations. So how we get to these numbers, right? How we can produce this? The core insight by the authors is that the structure of the tree, right, that we built is the same as binary search tree, right? And there is a nice result, right, from the research on binary search trees that the average depth of the observation in our tree is the same like the length of an unsuccessful search in the binary search tree, right? So, and that can be approximated by this nice formula. Like you can look it up in the paper, but basically the main insight is that we take the average, right, depth in our tree, and we divide it by what would be the theoretical average depth, right? And we use that as an exponent in the exponential function. So basically, if our average depth of an observation is about the same as the theoretical, this would turn into -1 and we get 0.5. So basically, if our observation is about the same as what we would expect on average, there you go, you have this 0.5, and therefore that's why you have that would not be an anomaly. However, if your average depth is much smaller, the observed one, right, the one that you get from the isolation forest, if the average depth is much smaller than the theoretical one, you exponentiate this to like you would get 2 minus say 1/10, right? And therefore you would get something that is closer to 0, and therefore you would get, 2 to the power of minus something very small. You would get close to 1. So when you plot this in a 2D density plot, right, or you see these contours, right? That the kernel of the observations is really like, here is 0.5, but the further you go from that kernel, the score gets higher. There was recently some paper, I think, coming out about like smoothing these edges, right? Because they can get too kind of sharp, right? So they were like smoothing that a bit to alleviate it. So the nice thing about this is that you are estimating the density, right, by an algorithm that deals very well with categorical data, can crunch potentially highly dimensional data set. It can be can deal with even missing values, right? And can be well distributed, right? Does not have assumptions about, or does not have the like typical assumptions about the shape of the distribution, right? So it's non-parametric. So it's much better and more generally applicable than just assuming, for instance, normality, as I said. Like I'm not claiming that this is the typical approach that people would do, but on that contrast, I just want to emphasize like how general this method is. So in practice, what you do, and please feel free to ask a question. That's Kuba. Even wait till the end. So what you do in Python at the end is, and in R it looks pretty similar. Here we just import some file, right, and we call isolation forest estimator. We just give it the number of trees and the random number seed. And what we get, and then you call predict, right, on new data. And what you get is this predict and mean length. The predict is the score that I described, the normalized one, right? So this one is pretty below 0.5, right? So this is, not anomaly. And the mean length is 6.82, which again, it's rather deeper in the tree, right? An anomaly should be somewhere at the top, right, close to the root. Okay, any questions to this before I go to the tree API?
Yes,
please.
H2O also gives us the GLRM algorithm for anomaly detection.
Generalized low-rank models, yes.
Yeah, and I used it. It looks nice. So can you very, very briefly compare and contrast the isolation forest and GLRM?
Right. So the GLRM is a method how you can project your original potentially high-dimensional space into low-dimensional space, low rank, and you can then project it back, right? So this is great for data imputation, for data compression, right? This is really, really specific, and GLRM is also great that it can work with all sorts of data modalities, right? Like categoricals and numericals. So that's, I think, why it's so strong. However, this one, right, is really proposed and designed for one specific purpose, and that's only to detect anomalies. It does one job and one job only, right? GLRM is a multi-purpose thing. You can, very often people use also autoencoders, right, for anomaly detection.
Autoencoders, yes.
That can also be there. But this thing is also very fast, right? Because you partition the trees randomly, essentially, right? So it's very simple. Okay, the tree API. So this is not really machine learning related per se, like that directly. We are not learning something here, but we are rather looking into what we have learned, right? So tree-based methods these days are amongst the most used, right? The GBMs are perhaps the most used or most popular in Kaggle competitions, if not the most used. The same with random forest, or similarly with random forest or extreme trees. And there's a rising interest in explaining or interpreting of AI and machine learning, right? There's basically a stronger and stronger demand by even wider public these days. I read that even in the news that basically people are getting realized, oh, we are surrounded by machine learning and we want to understand why somebody is going to get a credit, for instance, right? And these are very important issues. So the first thing that we need basically to provide to enable this is to actually give an API to users so that they can actually really inspect the results of those models. So this is basically motivated why we came up with this tree API. And what it allows you to do in both R and in Python is that you can basically traverse, you can get the tree, right? So say you train an ensemble of 100 trees in in a random forest or gradient boosting machine, and you can then basically pull each of these trees and look at it, right? And plot it, for instance. So it's very simple. In R, as it should be, right? In R, you just run get model tree. Here is your model. That could be GBM instance or random forest. Here is the number of trees. R starts the numbering with 1, right? So you start with 1, 2, etc. In Python, the API is similar, but here it's a constructor of a class H2O-3, and you start the numbering with 0, right? If you are running a classification that has multi-classes, not just the binary, right, but multi-classes, then the model in fact creates multiple trees for each of these classes, right? So for each of these categories, so there you need to specify also which particular class you are interested in, right? Okay, I don't expect you to basically read through all of this, but what is the main takeaway from this slide is that the H2O-3 that you get from the methods that I showed on the earlier slide, you get basically left children, right children, right? And that's the array that describes the full tree, right? Or you can get a root node, which is a pointer, right, or a reference to H2O split node, right? Which also contains left child, right child, and recursively you can follow these pointers towards the leaf nodes. that has only ID and the prediction, right? So how do you traverse the tree if you use the global structure, the H2O-3, right? So the node number is the index, right? So this is an example from, I believe, R, right? So the index 1, 2, 3, 4, 5, 6, 7, right? And you see that the left children of row number 1, which is the index 1, is 2, and the right children is 3. So we see 2, 3, right? Then you can look at the index 2, right, which would correspond to this node. And again, it would be 4 and 5, right? So that's one way how you can go through this. An alternative way would be, as I said, this recursive following to these pointers, right? So let us assume that we have this tree. This split node is the root node, right? The root node is also a split node. And let's say that we want to follow this branch towards the leaf node. So all you do is that you get the tree, you get the root node. This is an example in R. Left children, right children, prediction. There you go, right? In Python, it's the same. You just don't use the @ signs. The @ signs is the access to the slot in S4 classes in R. The same is in Python. You just use the classic object notation. Okay, the last thing that I want to show is how you can use this for plotting. It's just the result, just a little teaser. Because you can't do plot H2O-3. Maybe it will be available in the future, but as for now, it doesn't come directly in H2O-3. But my colleague, Gregory Kaniewski, on this blogspot, on this blog, noviden.blogspot.com, shows how you can do that very easily by basically using the tree API. So basically all he did is that he used the tree API to construct a graph, right, that he passed to a package, I think data.tree in R that then made this. I think there is another way how you can plot the tree by extracting module and generating a graph with .file. But this is directly in R. And you get, as I showed you, there's the main structures there are the left and right children, but there's a lot of information about the features, the splitting points. So you can then get this nice tree of basically how the decision went, each branch, what was the decision, right? Which way the NAs go, which is also important. If there is a missing observation, does it go towards the left or right branch in this tree, right? And then the eventual predictions. So that's really it. Like, do you have any question with this?
I have a quick question. In
Please.
the category of explainable AI, where are SHAP values on the H2O agenda? Are you guys discussing getting Shapley stuff into the library?
We have that, and we have that on our roadmap. It's definitely this year. But I would lie if I tell you if it's Q1 or Q2. But it's on the roadmap for this year. Definitely. It's in driverless, right? But it's on the
Okay.
it's you have Shapleys and limes and basically
Yes, I know limes.
all sorts of others, K limes, and there's two different limes. But Shapleys for open source are coming as well this year.
Okay.
On the roadmap. At least that was the state also in the H2 world in London.
So if you've got a XGBoost model saying it's made of 50 trees and the results are averaged to make the inference, right? So you've got 50 of these.
Yes, you've got 50s of these, and then you average over. Depends on whether it's a gradient boosting or random forest. In the random forest, you would average over those ensemble. In gradient boosting, you actually do that progressively through all of those.
So I've got 50 of those. How does that help me the challenge we have? Does that help me interpret the fact that I can pick apart the tree structure and re-understand it? Okay, I've got 50 of those. How does it help me?
Right.
With a customer trying to explain to them how its predictions.
Right. Yeah, that's a good point. So this is one way, right? I'm not saying the best or the only, but if you want to visualize the trees, you need an API, right? So that's why we built the API. I'm not saying that this is the best way how you do an interpretable AI. In that case, I would rather say it's not. You need other measures like Shapley values that gives you actually theoretically well-founded contributions towards the decision to each and every prediction, or you can average over the predictions and you get a global kind of measurements of which factors and to what degree influence the decision.
Feature
right?
importances.
So it's like the feature importances, but they are all, feature importances are only magnitude, not the direction. Shapley's also give you the direction, right? So Shapley's or Limes would be better way in this, like if you look at the global picture, right? Or what you can do, and that's what we do also in driverless, right? Out of the box, what you can do is that you actually build a simpler model, right? Surrogate model. So you've got a complicated ensemble and you were very happy with it. It's a very precise model, hard to interpret. So what you can do is that you build a predictive model that explains the predictions of this complicated model, and you just build only one tree, just one tree. And it will be approximating the predictions of the complicated model to say with 90% precision. So it's 10% wrong, 90% correct in explaining the complicated model. Then you plot this surrogate model that is just, one tree with this API. And this also gives you some insight into what's happening. But you have to be careful, right? Because it's 90% right means 10% wrong. And that's of the model that has also some inherent precision, right? Hope that answered.
Yeah.
Okay, one last question, and then I want to be mindful.
Just a quick one, really. Does the target have to be categorical or also?
No, it can be, of course, it can be numeric. Yeah. Okay, thank you.